Yeah, so thanks for coming this evening.
Good evening, everyone. Ideas in science, and I think somehow particularly physics and mathematics, can take very long time to find their realization, their proper setting. For example, gauge theories that will appear tonight were conceived as a scale transformation, like the gauge of a railway, invariance under scale transformations, but it was a complex form that was really the rich version of it. Grassmann numbers, which are anti-commuting numbers, were invented by mathematician Grassmann, who was employed as a high school teacher. And it was 70 years later or so that it was realized that that's a natural description of the electron, as in the Dirac equation. And many ideas in physics that looked crazy at the beginning, particularly to the sort of rigorous mathematicians, found a later setting in rich fields of mathematics. One also can't be too short-sighted. Things can take a long time to get done. One shouldn't abandon them right away, and that's going to be one of the themes of Lance's talk tonight, perseverance. So it's wonderful to have Lance here. He's an APS fellow. He's a member of the National Academy of Science. He was awarded the Sakurai Prize and the Galileo Galilei Medal. Lance, thank you.
Thank you very much. It's a great honor and pleasure to be able to give a talk in front of this sophisticated audience. And I know they're sophisticated because there was no black holes in the title, but you guys all knew that behind every gravitational wave there's some black holes, so you came anyway. So, so I want to give you a kind of voyage of discovery, and really two separate voyages of discovery. One that takes place in outer space, way out there. I mean, normally astronomers look out there and they look at light or other kinds of photons and particles from electromagnetism. But about 10 years ago, it was discovered that one could do astronomy in a completely novel way using gravitational waves. And then I want to switch gears and talk about the very small. And I want to talk about results that have come out also about 10 years ago from a device called the Large Hadron Collider in Switzerland. And that device discovered, or a set of devices discovered, the particle called the Higgs boson. And then both of these stories have appeared in the press a lot, and people may have heard about them, but there's something that's not quite as well known, so I call it a secret connection. The underlying physics behind gravitational waves at the sort of most fundamental level, there's a very deep connection between what happens in the heart of a proton collision when you make the Higgs boson and what happens when these black holes spiral around. So those will be the sort of where we're going tonight. So in fact, as Mark was saying, these discoveries, which are kind of the essence of big science, took a very long time to develop. And they really got going both around the 1960s, although some have even deeper, much deeper roots. But from the 1960s to the time of the actual discoveries, it took about a half century. And some of it was to consolidate the theory and understand that this was really something worth going after. And another, on the experimental side, was advancing the technology required to make these amazing machines that could make these discoveries. So this is one of the sites that was involved in the discovery of gravitational waves. It's in the plains of eastern Washington, and there's another similar device in Livingston, Louisiana, and also Virgo in near Pisa, Italy, and a newer one in Japan. And just about 10 years ago, in September of 2015, there was a little burst of shaking, essentially, of the mirrors that were at the end of this device. I'll show you a picture later, but basically this indicated that something had gone thump in the night. And it was interpreted as two black holes suddenly merging and becoming one. And we'll talk about this in a little more detail, but this was a huge, shock that had finally been observed after a long quest. And it was so revolutionary that from 2015 to 2017, when the Nobel Prize was awarded to these three gentlemen, basically less than 2 years had elapsed. And we'll discuss them a little bit more in the future. But within about 3 years earlier, there had been another revolutionary announcement which involved another large device. That previous one has arms of about 4 miles, and it would sort of fit in here. You see this aerial photo of a laboratory called CERN and a big particle accelerator. They conveniently put the Geneva airport here as a ruler to indicate how ginormous this machine is. This is the very tip of Lake Geneva here. Anyway, at this region, there were two underground, very large detectors called ATLAS and CMS, and they reported on this day that they had found some bump here, which is in the decay of a particle to 2 gamma rays, and it was the long-sought Higgs boson. And again, just to indicate how revolutionary this discovery was, there was a Nobel Prize awarded as a result to Peter Higgs, after whom the boson was named, and Francois Englert, who also played a key role in developing the theory. And so that came, again, within a year or so. So it was pretty, two kind of very long voyages culminating in the discovery. So now I want to wind the clock back and tell you a little more, first about the search for gravitational waves. It all came out of a theory by Albert Einstein called the theory of general relativity, which we often call GR for short. And it happened just about 100 years before the discovery of gravitational waves, when he wrote in German, which was then the prevailing scientific language, an article which was quite long and had lots of argumentation in it. But at the heart of it, it just had two equations. Now, these equations might not mean much to you, so I'm going to use a famous physicist named John Wheeler to explain them to you. This equation says that space-time tells matter how to move. And this equation says that matter tells space-time how to curve. And the most important thing was that space-time was no longer seen as a kind of rigid, very flat structure, but it was dynamical and curved. And so the presence of matter kind of puts dents into space-time, and then things roll around and respond to the curvature of space-time through this kind of equation. So it's a very complicated system. It has all the richness of all the orbiting of planets around the sun in the solar system. And in the solar system, it only makes very small corrections. But if you are able to go into the right regions, it makes much more dramatic, has much more dramatic consequences. Now, within a month of writing down this theory of Albert Einstein, Karl Schwarzschild found something called the Schwarzschild solution, which was a solution to the equations that I showed you before, which represented a very, very dense star. And it was so dense or so collapsed that the curvature was so strong that no matter, not even the fastest moving matter known, which is light, could escape from a certain region beneath this horizon or inside a horizon. And actually Wheeler, I think, was the one who first called it a black hole much later. But these objects were known as mathematical solutions for a very long time. On the other hand, the evidence that they really existed in the universe took about a half century until roughly the 60s, when there started to be better evidence. Another Nobel laureate, Subramanian Chandrasekhar, has a quote which I really love. He said that the black holes of nature are the most perfect macroscopic objects that there are in the universe, because the only elements in their construction are our concepts of space and time. We think that these are created through the collapse of massive stars, and the massive stars are made out of matter. But once the collapse happens, all that matter disappears behind the horizon, and then everything is curvature of space and time, and through Einstein's equations. And while there had been evidence for black holes through various kinds of optical observations, you couldn't image them very close to the event horizon. But then through a consortium, an image of a black hole, a supermassive black hole, was finally made in 2019. But there are still very few of these kinds of pictures. And most of the evidence we have about black holes now comes through gravitational waves. Gravitational waves were predicted by general relativity, basically as soon as the theory was written down, but there were a few twists and turns. First of all, gravitational waves, as we'll see soon, they are waves, and they're waves in sort of the structure of space-time itself. So distances suddenly change and oscillate a little bit as these waves go past. They're little ripples, and they move outward at the same speed as light. And in order to generate them, it was understood very early on, you would probably have to take some extremely massive objects and accelerate them extremely rapidly. Now, it was quite subtle because there are a lot of subtle issues in general relativity, and the creator of GR himself, Einstein, actually doubted their reality as late as 1936. In that year, he wrote a paper that refuted the existence of gravitational waves, and he sent it off to a journal. And the journal sent it back to him because the referee actually knew what was going on and understood Einstein's mistake, and suggested the following revisions. And Einstein replied that he hadn't authorized the journal to show it to specialists before it's printed, which is pretty funny to those of us who have submitted many papers through peer review, but you know, it was a smaller field. He had a little bit of a reputation, so he usually got a pass, I guess. Anyway, that was it for him in that journal. So what I want to say also is, besides perseverance, you know, science is not completely linear all the time. Even great geniuses, you know, sometimes they have little issues. Now, gravitational waves are in many ways analogous to radio waves. To make radio waves, those are oscillations in electromagnetic fields. And the way you can drive them is by taking a big antenna, which is a way to drive current back and forth in a particular way. And those electric charges that are the electrons in the current, they essentially cause the generation of these electromagnetic waves. And gravitational waves are very similar in principle, except that the thing that you want to move is not electric charges. Any mass will do. It can be completely neutral. It's just that you should have a very large amount of mass, and you should move it very fast and technically accelerate it very hard. And if you do that, then you will produce waves which are now not in an electromagnetic field like radio or light, but actually in the distances between parts of space-time. This very faint curvature of space-time propagates out from where these black holes are going. So now, by the 1960s, the reality of gravitational waves were well accepted. And people could estimate how strong they would be, and it looked really rough. They were extremely weak. When a gravitational wave passes by LIGO, their mirrors, which are roughly this size, 1 foot in diameter, they move by an incredibly small amount, like about a 10,000th of the diameter of a proton. And a proton, as we'll see, is not very big. So expressed as the size of the mirror, it's about 1 part in something that has 18 zeros. I don't even know how big this number is. There's probably an official Greek name for it, but I don't know it. Anyway, I just say it's way less than a gnat's eyelash. So you have to measure this to an incredibly ridiculously small amount. Nevertheless, some people were up to the challenge. And one of the heroes of this story is Ray Weiss from MIT. He had fled the Nazis as a kid, and he grew up on Manhattan's Upper West Side, repairing people's radios. I learned, researching this, that Manhattan was divided, and it was AC on one side and DC on the other side. And you wouldn't believe how many radios wouldn't work when they crossed that divide. And so he started doing that, and then he started building his own hi-fi systems. But it was like a tinkerer, and he only sort of went to MIT to understand some of the theory of these devices better, got a girlfriend, flunked out, later struggled to get tenure there. I don't know if a girlfriend was involved for that one, but anyway, he came up with the basic design, which was polished and improved over decades. But it was the idea to use lasers, which had only recently been invented, to store light in these long cavities and have some fancy mirrors here that have to be controlled and suspended with incredible care. And eventually you read out, the readout comes from a photo detector. But essentially when a gravitational wave passes through, it changes the distance very slightly between one arm and the other arm. And that change in distance, it gets read out optically by a change in the amount of light passing through. So he came up with this idea, same basic concept, became LIGO. But of course, there are many, many challenges. A little bit later, Caltech joined forces, and another hero is Kip Thorne, who was born in 1940 in Utah, about as far as you could get from Manhattan, I guess. And he was an undergrad at Caltech and a PhD at Princeton with the same John Wheeler, who had a way with words. And he became a full professor at Caltech by age 30. And Kip is quite the polymath. He authored a textbook, which I read as an undergrad and again as a grad student, with also John Wheeler and Charles Misner. But he also authored a popular book, and if you want to learn more about this story, you may want to pick up Black Holes and Time Warps. And furthermore, he wrote at least parts of a screenplay for the movie Interstellar. So here he's explaining general relativity to Jessica Chastain. But I don't know if there was a quiz after that. So this, I don't expect you to read all of this, but this is the official LIGO timeline at the LIGO website. LIGO stands for Laser Interferometer Gravitational Wave Observatory. And it was funded, has been, and is still funded by the National Science Foundation. And it was a collaboration between Caltech and MIT, although other investigators have joined since then. I was actually a Caltech undergrad, and I took classes from Kip Thorne, methods in classical physics, and one of the homework problems involved some stupid interferometer. No idea what this thing would ever be used for, because it was like at least 30 years later before they were able to make this detection. And anyway, this same National Science Foundation here, it also funds the KITP. So they've played an important role in lots of different kinds of science. Nowadays, LIGO has over 1,200 scientists, collaborators working on it, and there are also other gravitational wave observatories with similar numbers around the world. Now, to organize these things and to design something that has a huge amount of engineering challenges as well as science, you need somebody with that kind of science leadership. And so the third person who got the Nobel Prize for the discovery of gravitational waves was Barry Barish at Caltech. And he also was born in the US, but to recent immigrants, and he grew up in Southern California and got his degrees from Berkeley. And he came out of experimental particle physics, which has a history of very large collaborations. And ironically, he was leading a large detector collaboration at what we called the superconducting super collider in Texas, but that project was canceled, and it was to LIGO's benefit because he headed to LIGO after that. So now I just wanted to mention that there are two LIGO detectors in Hanford, Washington, and Livingston, Louisiana. I'll point out this is down by the bayou near the Gulf of Mexico. Yes, right, okay. So in order to reduce spurious signals, a very powerful control is if you have essentially the similar waveform happening at the same time in two different places. Because there's an incredible amount of noise you're trying to beat down, but the noise is highly the noise here has nothing to do with the noise here. So if you can see the same blip above the noise in both places, that's your number one hint that it's a real signal. Also, you can get an idea of where the signal's coming from by how much time elapsed between these two locations. So this is a little more of a picture of what happens when two objects that are very massive get very close to each other. You can't do this with ordinary stars. Stars are too fluffy. They will run into each other, and they will never make a strong enough signal. You have to wait until the stars collapse into something much denser. One thing is a black hole, and the second object is called a neutron star, which current KITP director, that's his forte. So I'm treading on his turf a little bit here, but at my peril. Anyway, you bring two of these things called compact objects because they're extremely dense. A neutron star is the mass of the star in the size of San Francisco, roughly. It's squeezed down so far. And black holes are even denser and more massive. So anyway, you can bring those together, and as they orbit, they actually radiate enough gravitational radiation that it causes them to come closer and closer and faster until all of a sudden they join in a big burst. And so what you get is a wave signal, like a radio wave, but it keeps increasing in frequency, which is called a chirp, as some members of the audience who've worked at Raytheon know. So, but I was looking for the sound, but I couldn't find it. So I'm going to do my impersonation of a gravitational wave. Sounds kind of like... Anyway, that was pretty lousy. But if these are two black holes, this part here cannot be seen by LIGO. You can only see the very last bit. So here's what that first signal looked like. It just lasts less than a few tenths of a second, and but it was very distinctive in its pattern, and they ruled out many other alternative things and announced that observation. Since then, they've seen hundreds of these events, and almost all of them look vaguely similar. There's lots of different cases, but they kind of look similar. But there's this one outlier here. This one outlier was two neutron stars coming in, and because they're much lighter, they are visible. Their blast stages are visible for a lot longer. So there are many, many cycles here. This is 40 seconds long, whereas most of the other ones are a few tenths of a second. And this one was also seen optically. Neutron stars have a lot of neutrons not hiding behind a horizon, and they get shredded and come spewing out, and then there's a huge explosion called a kilonova. And these were seen with telescopes after the first indication came from LIGO. So whereas nobody has seen any of these except in gravitational waves, except for this one. So this is what we know about observations of black holes now. And these guys out here, these were usually earlier, and they were done using electromagnetic techniques, optical or X-rays and things like that. And these guys down here are so light, these are neutron stars, And we don't think neutron stars can be above about this line. So everything up above there is most likely a black hole. And all of these events are from LIGO. And what you see for these, you see two guys here and then one more. So you have two initial ones, and you can measure their masses. And then they come together, and you make a third one. So most of our information about black holes is now from LIGO. And this is called the stellar graveyard because it's after stars do their burning that they tend to collapse into these black holes and neutron stars at the end of their lives. Okay, so we did part one. Now we're moving on to part two. We're going from the very large and distant, sort of astronomical, down into the heart of matter. We're going to talk about the search for the Higgs boson. And the Higgs boson represents, as we'll see, the last piece in a theory of matter and subatomic forces. And it really took about 5 decades from its conception in 1964 until the discovery in 2012. Now, a lot of that time, it wasn't quite clear what to do about this Higgs or whether there was any chance of ever seeing it. So the experimental searches began somewhat seriously in the 1980s and more seriously in the late 1990s and the first decade or so of the 21st century. And so it took a lot of time in order to find this kind of holy grail. Now, I'm not going to be able to explain to you all the science, but it's important to note that Peter Higgs had this idea while walking in the cairngorms of Scotland. So I highly suggest that. Although I haven't had as much success as he did. So it requires a new particle, which has come to be called the Higgs boson. But it's also important to notice that as in experimental science, where it sometimes takes thousands of people to make a discovery, in theory, often the same ideas are percolating at the same time. And so maybe the Higgs boson could be known as the Anderson-Brown-Ungler-Gerolnik-Hagen-Higgs-Kibble boson. But you'll excuse me if I just call it the Higgs boson from here on out. But again, more people are involved than often things get summarized in. So now we're going to take a deep dive into the heart of matter. Here's a sugar cube here. If we zoom in by a factor of about 100 million, then we could see, in principle, the atoms. For example, there's hydrogen inside sugar, and the hydrogen atom has an electron traveling around a proton. And that proton itself is quite small, too. But first of all, the size of the atom is set by the electron and how heavy it is. It's actually a lot lighter than the proton, and it sort of controls the size. Without mass, this electron would fly off and atoms would not be stable. And one of the questions that Peter Higgs was trying to answer was, where does the mass of the electron come from? Okay, maybe it's slightly down the road, but it was along the same direction. If you zoom in by another 100,000, now you can start to see inside the proton. And this was actually done at the lab I work at, SLAC, back in the 1960s. It was discovered then that the proton was made of hard objects, which were dubbed quarks. And these quarks also have masses. And so there's another question, where do the masses of the quarks, in this case they're called U or up, D or down, and there are other quarks, where do they come from? These were the kinds of questions about the origin of mass that Higgs and the other physicists working then were trying to elucidate. Now, we have particles of matter, but there are forces between them. We talked about electromagnetism and gravity. There are actually 3 known subatomic forces. And one of them is electromagnetism, and we'll come to another one of them in a little bit. So electromagnetism is the force that holds atoms together. There's an electric charge for the electron and the proton, and they interact through electromagnetism, and that holds atoms together and governs most of the structure ordinary materials that we see. So, but electricity and magnetism, when you vibrate things very rapidly, like we discussed for radio waves, or even faster in atoms, you get out light. And, but we also have a description of this in terms of particles, and we say that electromagnetism is a force that is carried by a particle called the photon. And it's a quantized packet of light. So this is thanks to quantum mechanics. Quantum mechanics is a very strange theory, but it says that sometimes it's useful to think about things as particles, and sometimes it's useful to think about them as waves. I don't know if you guys have managed to bend your mind to see that this is particle, and it is also wave. So this exhibits visually the duality of light between particle and wave. And it's extremely important when you start talking about things in subatomic physics. Now, if we didn't have any mass for electrons or quarks, everything would look very different. For example, the electron mass, that sets the scale for atoms. If we drop the electron mass to 0, the atoms would basically fly apart. And so it was very important to try to understand what was going on there. This is a little illustration of how we think about forces in the subatomic world. We think of things bouncing off each other by exchanging particles that are, we call bosons, specific particles. And the particle of electromagnetism we call the photon. And so Feynman taught us how to draw diagrams to illustrate these sort of trajectories. As two electrons scatter off each other because they both have electric charge, we say that they exchange photons. And we can describe many, many subatomic reactions using these kinds of diagrams. To know which things are allowed, you have to take a course in particle physics. But I'll give you the short version of it. First of all, these are all the fundamental particles that we know about and we can deal with in the lab every day. Some labs, some special labs for some of the particles. They include the particles, the electron over here. It has some mysterious cousins. We don't exactly know why they're there, but they're very much like the electron, but heavier. And then the particles inside the proton were the up quark and the down quark, and they also have heavier cousins. And then there are very ghostly neutrinos over here. So these are the particles of matter. It turns out they all have the same quantum mechanical spin, and we normalize and call it 1/2. And then these bosons, the particles around here, have spin 1, and we call them bosons, and we think of them as carrying forces. And then the Higgs plays a central role there in the middle, and it's the only particle here that has no spin at all. And that chart kind of shows you something about the organization, but if you really want to know in detail how the particles interact with each other, you can take a course for about a year or so, and then you will see and understand better some of this. But the main thing I want you to take away from this, it's the Higgs boson in yellow. It talks to many, many particles. It talks to many particles that we were discussing before, but it would take a while to go through the whole thing. But it's a central particle, not only in this picture, but in this picture. And so it was very important to try to find it. To try to find it, we use another one of Einstein's equations, which you might have heard about more than the two of general relativity, and that was E equals mc squared. That equation tells us that all matter contains energy stored in its mass. For example, a huge amount of mass is stored in the nuclei, especially when the nuclei change from one form to another, and that gets released can be released in nuclear energy or nuclear weapons. But you can also play the game the other way around. You can send in a lot of energy by accelerating particles like electrons or protons to very high energy, and then you can make new heavy particles. So that's the general game that people play at accelerators. And the Higgs boson is one of the heaviest, the second heaviest particle we know, and it takes a lot of energy to make it. Let's now wind the clock back to the late 1990s. The Higgs boson was already a well-known constituent of the Standard Model, but it was understood that it was going to take a lot of effort to find it. And all the other particles of the Standard Model except the Higgs boson had already been found. So it was the big holdout. There were actually some ways to get an idea of how heavy the Higgs boson was, and it was suggested that it could be within the range of 3 large particle accelerators. I'll mention 2 of them here in a second. And at that point, the direct search really began in earnest. The first of those 3 accelerators was a ring, and you've seen the same ring in a previous slide, but in this case, a different machine was installed in the same tunnel. And that one involved electrons and positrons. And electrons and positrons, they are very clean machines. If you make something there, it's not so hard to identify it. And you could actually see the Higgs boson, and this is some Feynman diagram that tells you that this Higgs, when you make it, it comes along with another pretty well-known particle by then called the Z boson. And so this process was extremely well understood and very clean. But the bad news was the Higgs was too heavy. So there was not enough energy in these collisions to make it. So it got actually pretty close, but no cigar. And but by the year 2000, it was well understood that the Higgs should be heavier than this, but also a little bit lighter. I mean, not that much heavier, or the Standard Model was wrong. And there was a machine at Fermilab in Illinois, but it was not quite able to make the Higgs boson in enough quantities to detect it. So instead, the frontier for Higgs physics moved to the Large Hadron Collider, and that was installed in the same tunnel after the other machine was removed. So that took about 8 years or so. And this machine started operating in about 2008, and it's still going. And it took about 4 years to find the Higgs boson. So the Higgs boson data was collected at these 2 regions, and there are several regions where the protons collide at the Large Hadron Collider. Now, these colliding particles are much more complicated than electrons. They're bags of quarks and gluons. And so it's very complex to dig the Higgs out of this. This is an example of the Atlas detector in an intermediate stage of construction. And so this inner area gets filled in later. I just show this picture with the human here to give you a sense of scope of how big these detectors are. And they're multifaceted instruments, and they make the LIGO collaborations look small. They have like 3,000 scientists or more working on each of these because they're such complex devices, and the data coming out of them is so complex. And it's an incredible fire hose too. 20 million times a second, you get protons colliding, and you get 25 to 100 simultaneous collisions. You can actually see them reconstructed here. The tracks come from about 20 different locations along here. And you have to look at find the interesting collisions and determine what they are. And you can't even keep most of the collisions, so you have to decide which ones to keep and which ones to throw away like that. Here's just a few events. This one is compatible with being a Higgs decaying to 2 photons, shown in green here. They leave a lot of energy further out. And here's 4 muons, which is another way that the Higgs can decay. So after collecting all of these events and analyzing them in the first 3 or 4 years of operation of the Large Hadron Collider, the discovery was announced. They had enough evidence that the probability of faking it by a statistical fluctuation was just too low. And here you can see one of the discovery plots of finding a Higgs boson. And now, finally, we know what its mass is very precisely. And it's about 133 times the mass of the proton. We often use a different unit, but anyway, it was actually not too far away from the limit that made it too heavy to see at the earlier collider. So missed it by that much. And I also want to point out that the leader of one of the experimental collaborations at the time is a professor here at UCSB, Joe Incandela. And other major contributors to this discovery were having a good time at the press conference. Okay, we made it to part 3. I'll try to wrap up quickly because I know you guys will have some questions. So part 3 is that there's a secret connection between the rules that underlie the generation of gravitational waves and one of the forces that controls collisions at the Large Hadron Collider, including the production of the Higgs boson. So this guy you probably know, Albert Einstein, and this is C.N. Young and Robert Mills. And we'll come back to them in a second. This is what happens if a theorist takes a microscope and tries to describe what's happening inside the LHC. Pretty simple, huh? Actually, it's a big mess. This might be a Higgs boson that's produced. And you should sort of understand that the stuff in here happens very inside, and then things come out. And when things come out, they get very complicated. So we theorists can compute what happens inside here, and we feed those predictions to the experimentalists, and then they check to see what that means in terms of Higgs bosons or other phenomena. And the stuff out here, we have to learn how to deal with it. There's some things we take from experiment having to do with the structure of the proton and how the quarks and gluons are confined in there. And there's other stuff coming out here which you might think it was important, but if you deal with it properly, you can kind of not have to worry about it as much. But it's still very tricky. And all of this complications is caused by a theory which involves the strong force, the same force that holds those quarks and gluons together, and it's often called quantum chromodynamics, because the chromo, Latin for color, there's like a charge, like an electric charge like color. But it's often also called, or the general case of it is called Yang-Mills theory, after C.N. Yang and Robert Mills. And the force is carried by a particle that naively looks a little bit like a photon. And the difference, though, is that it has a nonlinear interaction. If you take a photon and ask whether it can convert to 2 photons, the answer is always 0. But gluons can do that, and that makes all the difference. Gluons are actually inside the proton in abundance. And because they're so copious in there, they're the best way to make Higgs bosons. They actually utilize the heaviest particle in the standard model, called the top quark, as part of the production. And then you can see, say, the Higgs decay to photons afterwards. Now, I want to point out that gravity is another nonlinear theory. For example, when you send light around the sun, you might know that it gets bent. And although it's never been observed, everybody believes that gravitational waves would also get bent by massive objects like the sun or black holes. And if we think of the gravitational waves as a collection of particles, remember, light is a particle, so gravity should be a particle too, not only a wave. These gravitational waves, we can also think of them as particles. And the bending of these particles is through the exchange of a force carrier, in this case, not the photon, but a graviton. And this bending of light tells us that there's a nonlinear interaction between gravitons. And that nonlinear interaction looks somehow very similar to the Yang-Mills case, to the interaction between gluons. But there's one little twist, which is gravitons are a little different from gluons. They actually have spin too. And this is how a test mass would move in a gravitational wave of one polarization versus another one. And the difference, you can kind of see it's at 45 degrees. So that one you've never seen before. but you have maybe done an experiment with polarized glasses and put them perpendicular to each other, and you've seen that blocks all the light. And that tells you that things change from one polarization at 90 degrees, from one polarization to the other polarization. And the fact that it happens at 45 degrees here, that's a clue that gravitons carry twice the spin of gluons. So we're almost done. We just need to notice that gravity, there's a sense in which this force that controls the universe at large is like the square of the subatomic nuclear force. Or we say gravity is the square of Yang-Mills theory. Now I've drawn this in terms of pictures which probably don't make a whole lot of sense to you. So I've given you an equation to remember it by. Okay? So that's all you have to remember. But some people like pictures better, so we'll just write Einstein is the square of Yang and Mills. Okay, so now you guys know something called the double copy, which hardly anybody knows about. That's the secret. This same relation, or generalizations of it, have been found to hold for an arbitrary number of gravitons scattering off each other. So it's not like a fluke that it only happens when you have 3 of them. It happens for any number of them. And here's the amazing thing. You can actually use these mathematical relations to, inside of black hole scattering or interaction, in order to help predict gravitational waveforms more precisely. And this is part of a program that will eventually feed in to understanding better the kinds of masses and spins of black holes at LIGO. But the bottom line for you guys is that inner and outer space are secretly related. And we're almost done, and people are getting antsy. So I will just say there's a rich spectrum of things to be done in astronomy using gravitational waves, also testing Einstein's theory, and there's a lot to be done in studying the Higgs boson further. So there's a rich amount of science out there. And I want to also say that this is big science, and it takes a long time, and you need a lot of visionaries among the scientists. But you also need far-seeing national governmental agencies. NSF funded LIGO when it was known that the first phase would probably not discover anything, but they could see it through to the future. Also an international laboratory. Sometimes it's beyond national boundaries. That's CERN, to which the US also contributes. So in summary, I want to thank you all as taxpayers for enabling this journey. Thanks.
Thank you, Lance. Yes, question here.
I noted that, let's get the microphone, the graphic, hang on just a minute, let's get the microphone to you. I noted that the graphic representing gravitational waves took a spiral shape. Is that thought to be the way it projects out from the event?
That's a good question. I mean, it does come out roughly in that pattern, but I'm not going to swear it's exactly in that pattern. It's also supposed to kind of represent the fact that the particles are spiraling, the black holes are spiraling in. As they emit the radiation, they move down into lower orbits. But whether the wave actually looks exactly like that, I'm not quite sure. Maybe Lars knows. Yeah.
To expand on that, I heard you say that gravitational waves travel at the speed of light.
Yeah.
But you're suggesting here that all photons are linear and gravitational waves are non-linear.
Right.
Still traveling at the speed of light.
Well, they, first of all, there's actually experimental confirmation of this, because in that binary neutron star event, there was an optical detection of gamma rays around the same time within about a second. And these were like hundreds of millions of light years away. And so the speed is good to, 1 part in 10 to the 15, I don't know, some incredible precision. That statement's actually been tested. Now, the nonlinearity means that in principle, both light and gravity, they don't necessarily come completely straight. They could be lensed or bent around, but they should be bent in the same way. So it should not affect this. That's part of something called the principle of equivalence, which underlies general relativity.
Yeah, so staying with that thought about the curvature of space-time, our universe is three-dimensional, right? And so at what point can you tell the direction of these collapse events if you only have 2 points
That's great.
between these two detectors?
There's some more information in the waveforms besides the delay. If you only have 2 points and that's all you know is the time delay, you get a cone. So there's also, when LIGO is operating, Virgo has generally been operating at lower sensitivity, but it's still there, and it provides some additional information. And with 3 points, you can intersect cones from the pairs, and you can localize it. It's not perfect because of the experimental uncertainties, but and the localization depends a lot on how loud the event was. If you have a weak event, then you don't get a nearly as good a localization. Or if one of the detectors was down, you get much worse localization. But you can still localize somewhat with 2 detectors by making some more sophisticated analysis of the waveform.
Yes.
By the way, there's actually a gravitational wave app you can get if you want to be the first to know when an event comes in. Because they have to alert astronomers to know if they're going to move their telescopes. But you can benefit from that.
Have we observed gravitons? Have we actually seen them?
So we have not seen gravitons as quantized particles.
Okay. And that was...
I personally believe that through this duality, that when you see a gravitational wave, it represents a very large number of gravitons. But you can't, they're too weak to observe a single one. People are trying to do some kinds of experiments in quantum gravity, but I don't think anyone has, successfully done that so far.
So if we were to find them, how would they fit into that diagram of the standard model in that list of particles?
That's a great question. Because the reason why they're not, there's some different reasons why they're not on that chart, which is that there's no universally accepted theory that involves both quantum mechanics and gravity. I used to work in string theory, and it's a very nice, consistent framework that does a lot of great things, but it doesn't make such concrete predictions. So, it's hard to say experimentally that is necessarily the right way to go. And so that's like one of the reasons it hasn't been incorporated yet into a picture like this.
Thank you, Lance, for a great talk.